lemma. What you want to think about is somebody's given you a pseudo-reductive group in the abstract, and you want to get some handle on it somehow. Okay, and the question is, what do you grab onto? Okay, all right. So suppose G is pseudo-reductive over K, and X inside G is a closed subvariety, is a geometrically reduced. Geometrically integral closed subvariety, such that when you look at it geometrically, it consists of unipotent points. Okay? And let me assume that it contains 1. So then I claim X is itself trivial. Okay? So let me just tell you some nice consequences that this has. So the proof of this is actually, see how we're doing on time. I'm basically, OK, so the proof of this is actually very short. But let me just tell you, I'll just list 4 nice properties that follow from this. So first of all, this allows you, so let me just say, so this allows to bootstrap properties from the geometric unipotent quotient. Okay? So over the algebraic closure, you can kill the unipotent radical to get a reductive group. And now I'm just going to list 4 simple properties that are reminiscent of features of reductive groups that you can bootstrap from that quotient by using the magic lemma. OK, so the first one is that for any k torus S in G, the centralizer is again pseudo-reductive. Remember, that was one of the properties you saw in the reductive case as well. The centralizer of any torus is again a group of that type. So that makes possible inductive arguments. And more specifically, for a maximal torus, T in G, the centralizer is generally bigger than the torus, but at least it's commutative. Okay? So I said that the commutative objects we don't really understand, but they exactly show up as the Cartan subgroups. Okay, so that's one good property. Another property is that if you start with any algebraic group, you can always form its commutator subgroup, and that's always Zariski closed. But then in general, you might have to keep iterating until the process stops. And it's an important fact in the reductive case that the commutator subgroup is its own commutator subgroup, that the process stops. And same thing here, that if you form the derived group, the commutator subgroup, that this is its own derived group. Okay, and that's also very important. And suppose I give you 2 maps, F1 and F2, between 2 pseudo-reductive groups. So these are homomorphisms, and I tell you that the induced effect on the maximal reductive quotients are the same. So suppose maybe these are, let's say, surjective maps for the moment. You can avoid that, but just for simplicity. So suppose I tell you that the induced maps, you get induced maps between maximal reductive quotients. If I tell you these are the same, then the maps themselves were the same. For example, if you're studying isomorphisms, which have the same effect on the geometric reductive quotient, that's this guy, then in fact the isomorphisms were the same. So you can detect things about equalities of maps by working geometrically as well. Okay? And then the last thing I'll say is if you look at the set of weights, non-trivial weights of the torus, maximal torus acting on the Lie algebra for the reductive group, that's actually the same on the reductive quotient away from let me just say, some characteristic 2 situations. Okay? So the point is that if you look at the weights of the non-trivial weights of the torus acting on the Lie algebra, it's actually a root system. okay? Precisely from the reductive case. So again, modulo certain problems in characteristic 2. So the point is that, and again, the proofs of these come very, very early in the theory. They don't require any complicated constructions. They only require the magic lemma. But this is at least to convince you that there actually is a possibility of getting your hands on these things. Because we have the fully developed geometric theory over k bar, we can try to pull up some properties. Okay? So next time, I'll describe a kind of general construction process and tell you a bit more about the internal structure theory. And then, as I said in Gopal's talks, he'll give you some flavor of how one shows that these particular construction, the standard construction, really accounts for most examples and what extra stuff you have to do to get everything else. Okay, so there is, in the end, a good internal structure theory as well as a close connection to the reductive theory. But if you're ever faced with studying a problem over an imperfect field, in some sense, the intermediary to accessing the reductive theory is to first go through the pseudo-reductive case. Okay? All right, I'll stop there. Yeah?
Maybe my question is a suit question, but how can the centralizer of the maximal torus be still commutative?
Be what?
Still commutative.
Well, it's going to be bigger, okay? So I'll just give you an example, okay? So for instance, so suppose I give you, let's take SLP, okay? And again, let's just say k prime over k is degree p, purely inseparable. All right? So inside of here, you have this Weber restriction of the diagonal. Okay? This is not a torus, because k prime over k is not separable. All right? The maximal torus, so inside of here, there's kind of secretly, there's a kind of natural copy of SLP already inside. It's sort of like, you know, the thing over the small field sits over the thing over the big field. Okay? And so already you have, maybe I'll call this diagonal k prime. And then you have the kind of diagonal over k inside of that. This is the maximal torus. This is actually its centralizer. So it's commutative, but this is not a torus. This is like the simplest example of a commutative pseudoreductive group. It's not a torus. But once you start taking quotients, it's very hard to describe those things. But that's like an example how it works out. But as I say, in general, the magic lemma actually yields this. You can kind of, to prove something is commutative, you just want to prove that its derived group is geometrically in the unipotent radical, which means you just want to show the derived group dies in the geometric reductive quotient, and then you can pull it up from the reductive case. Yeah.
I have a question.
Yes.
Is there a subclass of pseudo-reductive groups that quotients behaves nicely? I mean,
no.
or some
I mean,
field or certain field.
No, I mean, not. I mean, you can say. Yeah, I mean, the problem is if you quotient by anything, you know, smooth of positive dimension, I mean, it's not true. So, I mean, unless you're going to talk about like étale isogenies or something, I mean, basically the answer is no. I mean, quotient is just, it's really over every imperfect field. So this example that I described, I mean, it happens over every imperfect field, that you'll have a perfect thing with a smooth connected perfect normal subgroup and the quotient is not pseudoreductive. So there's no better fields for this sort of thing. Yeah. It's just, but so you just have to get used to not passing to quotients all the time. Yeah.
If there are no other questions, let's thank our speaker again.